So, the homework is due today, and then next week we will have our exam. So, again, the exam covers through the material related to sort of foundations of perturbation theory, including the ideas of non-degenerate, degenerate perturbation theory, and avoided crossings and all of that stuff. Okay. So, to make you feel better, although it really won't be necessary, you can bring 1 page of notes with you, 2 sides of a regular sheet of paper. But anything you really need, I will give you. Yeah.
Do you think, I guess I need to figure out what's on the lectures, but do you think we should bring the clutch board and stuff, or if you need it provided?
No,
okay,
okay, absolutely not.
Okay.
No. I won't, yeah, no. That's not the point here. Anything you need, I'll give you. All right, and so, trying to spend a little time reviewing things tonight so that tomorrow we can have a productive review session, okay? All right, so we are just talking about right now time-dependent perturbation theory. And so what we're looking at are situations where we have some system, like an atom, molecule, what have you, and we are thinking at the moment about applying some external forces to that system with some, typically thinking about that with some applied classical field, typically electromagnetic field, that interacts with the system. And this is the forces applied by my interaction are weak compared to the internal forces that bind the system together, right? And so it's in that sense that this is considered a perturbation. And what we're then interested in is how does this time-dependent force affect the dynamics of internal to the system governed by Hamiltonian H0. So we are looking to solve the time-dependent Schrodinger equation, and we did that in a particular way by going to the so-called interaction picture. And in the interaction picture, the operators evolve according to the free, like Heisenberg-like operators evolve according to the free Hamiltonian, and states evolve according to the interaction Hamiltonian. Okay? And so we have the time evolution operator in the interaction picture is generated by the interaction Hamiltonian in the interaction picture. And the formal solution we wrote down as the time-ordered exponential, which can be written as this power series in powers of the interaction Hamiltonian. Okay? And this is known as the Dyson series. So what we're interested in this case is are the transition probabilities whereby we imagine we start in some energy level of H0 with some eigenstate, the initial eigenstate u sub I, and we want to know what is the probability that at a later time we will find the system in some final eigenstate. Okay? Because it's not necessarily in that state with unit probability, but there's some probability to find it there. Okay? And that's given, according to this equation. That's the probability. You evolve the state according to the time evolution operator, and then you look at the probability to find it in that state of interest. Okay? And what we showed last night is that that can be re-expressed in terms of the interaction picture evolution operator. And so what we end up with is this power series in the probability amplitudes. So this C is just this matrix element. It's the amplitude to be in this state, starting from that initial state at time t. Okay? And this itself is a power series given by the Dyson series, right? So this, of course, is just, will be a delta function. And what we looked at last night was this term. So let's quickly review what we saw there. Okay? So if this is not the same state, to lowest non-vanishing order, we consider the first order perturbations. And to first order, this is then equal to just the integral at that final time t from 0 to t, dk, the integral of the interaction Hamiltonian in the interaction picture. Just getting rid of the primes now because we only have one integral. And when re-expressed back in terms of the Schrodinger picture, this looked like this. So that's just going back to the Schrodinger picture operator. And this we expressed as a Fourier transform of a windowing function times this matrix element as a function of time. So here, omega fi is the Bohr energy associated with the energy difference between the final and the initial state. Okay? And this windowing function is just a function which is 1 for t, this is a function of t, between 0 and the final time and 0 elsewhere. Okay? Right. Okay? So our transition probability amplitude to first order, what we see is it depends in some sense on the frequency content of this driving signal at the resonance frequency associated with the transition. Okay? That's the nature of the Fourier transform, right? To tell us how much of this signal, which is changing as a function of time, is at this frequency. So we see explicitly the phenomenon of resonance appearing here. Okay? And so this we wrote formally as the Fourier transform of the product of these two functions is the convolution of the Fourier transforms of this windowing function and that function. Okay? And this thing is just a sinc function. So it's the sine of that over that times that. That's what we saw with some constants out front. Okay? So, you know, this function has, if you know, we just plot it, of course this is evaluated at omega equals the resonance frequency. Okay? And this function, you know, is the usual kind of thing, which has a width in frequency space that is proportional to 1 over t. Okay? And then what we did last night, for our intimate group of people who were there, is to think about the particular case where my time-dependent Hamiltonian was associated with driving the system with a monochromatic or quasi-monochromatic source, right? So we wrote down the interaction Hamiltonian as a function of time as something that went like e to the minus I omega t. Now that's not Hermitian, so what we did is we said there's a piece that we call the positive frequency component, and then its Hermitian conjugate. And as I mentioned last night, you know, this is a jargon that has survived from the days of radio engineering, what we call positive frequencies and what we call negative frequencies. I mean, it's because in physics, of course, we like the e to the minus I omega t. We call that the positive frequency component. And then the thing that's the conjugate is called the negative frequency component, right? And this operator is a constant in this, in time. And it's the Hermitian conjugate of this, okay? So in this case, right, the Fourier transform of this is what? Well, we have the matrix element of this guy, and the Fourier transform of this is a delta function. It has only one frequency component. And the Fourier transform of that is also a delta function centered at minus omega. Right? So the convolution then, so the probability amplitude in first order perturbation theory, which is related to the convolution of this with the sinc function, looks kind of like this. So here's omega d, here's minus omega d. I convolve those two spikes with that, and what you find is something that looks like this. That should be symmetric, sort of. Okay? And I've drawn this for the particular case where omega d is big compared to the width here, which is to say that the time that I am driving the system under this, the way I've drawn it, is assumed to be big compared to a period of oscillation of the driving frequency. Otherwise, it's not in any way monochromatic, right? I need to have many oscillations for it to seem as monochromatic. And of course, the longer I interact with the system, the narrower this becomes. Okay? So when we do that, now I have to get the probability, I have to square the thing. Okay? And under this assumption that I've interacted long enough that my t is big compared to a period of oscillation, then of course the tails of this are 0, where this is non-zero, and vice versa. So there's no cross terms when I square it, and I just square each term to good approximation. All right? And so what we found then is that to first order, the probability to make this transition was the following. Squared omega fi plus omega d over 2 divided by f.
The denominators be squared?
They should. I keep forgetting that. Thanks. Double check. Make sure that. Right. Looks good. All right, so what did we interpret about this? Well, what we see here are these so-called resonant denominators, okay? So each of these terms will dominate for different conditions, depending on whether this under what conditions is this denominator small. The smaller the denominator, the bigger the contribution here. What we see here is that this term dominates when this is close to this, right? Whereas this term dominates when this is close to this. Okay? So the point here is that, I mean, since omega d is a positive number, that this term corresponds to omega, this being bigger than this. So that is to say that this corresponds to absorption. Whereas this term means that omega final is less than omega initial, so this corresponds to emission. So what we learn, one thing we learn here is that in this expression for the interaction Hamiltonian, the positive frequency component is associated with absorption, right? That is to say, having a situation where I started, this is my initial state, and this is my final state, and I'm driving the system that way, versus this, which is that I start in some initial state up here, and my final state is at a lower energy, and I'm driving the population down. And that's associated with the negative frequency component, okay? This is sometimes called stimulated emission, okay? Now, as we discussed, there's a couple of things I want to just review because some of you missed the lecture last night and we didn't have the video. One thing we see here is a notion of the time energy uncertainty principle. Okay? That is to say, the probability amplitude to drive the system from its initial to final state depends to some degree on how long I'm interacting with it. So, as we discussed last night, suppose I wanted to measure this energy difference. Well, one way to do it is to see what is the frequency at which I get maximum absorption. And then the energy difference is just h bar times that drive frequency. So the question is, how well can I, in an experiment, determine that frequency at which I drive the system up, right? Depends on this probability. But that I'm going to have some uncertainty of that because of the width of this spectral line. The longer I interact with it, the better I can determine it. So there is a time energy uncertainty principle, if you like. The longer you measure, the less uncertain you are about the energy difference. The shorter you measure, the more uncertain you are about the energy difference. Now this is a different kind of uncertainty principle. There's not, didn't come from the commutation relations, not like X and P. It's just Fourier duality, in a sense, right? Okay. Lastly, one of the things that we talked about at the end of lecture last night is the degree to which we should consider this perturbation theory. This was perturbation theory because, if we go back to the front board over here, we expressed the probability amplitude for the transition in a power series, which we assumed that each term got successively smaller, right? So that I can truncate it, and that would be a good approximation, okay? So when we look at this expression, it's clear that perturbation theory in this form, the way we've, at least I've always expressed it so far, will break down after some time because this probability, this expression will become too big, right? I mean, if we look at this expression on resonance, so let's look at the absorption probability on resonance. When omega d equals this, so then we get t squared good. Right. This matrix element. Just plugging that in. This grows quadratically with time. Right? The probability to in the excited state is growing quadratically at a time. Eventually, this thing just gets too big. It's no longer a perturbation. So this is, in some sense, has to be a short time expression. And as I said, often you'll see this expression taken to the t equals infinity limit in a very loose way, right? If we take the t equals infinity limit, if we look at, so if we consider, so let me rewrite this for arbitrary time, my transition probability here from initial to final state. Let me rewrite it as follows. I can write it as sine omega fi, or drive minus omega fi t over 2 squared divided by omega. This is what we have, the first order. If I just look at this thing, this sinc function, we look at that, let's come back to this board. As t goes to infinity, this thing gets narrower and narrower and narrower, higher and higher and higher. It becomes a delta function, right? This thing in the limit that t goes to infinity becomes, it has an area of pi underneath it, delta, a delta function, omega t minus that's what it becomes. Okay? And if you use some properties of delta functions, you can re-express this as 2 pi over h bar t, the matrix element of the interaction squared, times the delta function at omega e at minus omega I minus h bar. That's just playing around a little bit with the properties of delta functions. That is to say, you remember that a delta, this is equal to 2 over t h bar delta h bar minus h bar. Right? That's take the algorithms inside and outside. Right? So notice what we have here. We went from something that was quadratic in time through some sleight of hand to something that is linear in time. Without ignoring the fact that we took t equals to infinity, and what the heck did we do? We didn't take this to infinity. We just kind of ignored that. And then you look at this and you say, okay, so now instead of a quadratic rise, I have a linear rise. And now this looks like a constant rate. So we would say the rate of transition, or the rate of absorption, W, well, that's just the rate of change of the probability with respect to t. It's this. And this is sometimes known as Fermi's golden rule. But what the hell does this mean? first of all, we completely cheated when we took t went to infinity. And then, well, we have this delta function, the thing blows up anyway when we're right on resonance. So at this stage, and we'll come back to this in a couple of lectures, this is kind of a heuristic. We'll understand what this means and in what regime this makes sense at all. Because right now, it really doesn't make sense. But you'll see it derived this way often. Okay? And, well, it has some nice features. What you see here is that, well, unless energy is conserved, I can't make the transition because the delta function vanishes. I mean, this, as we will see, is a very kind of, I would say, classical-like notion of what time evolution is in quantum mechanics. It's a notion that thinks about what's real in the world are the energy levels. That's the real stuff. And everything else is just some jumping between those energy levels with kind of populations that goes. There's no notion of superposition here. It's just, it was here, and then it's there. And there's some rate by which that happens. And we'll come to understand why that, in what circumstances that is a reasonable way of looking at quantum dynamics, but it's not. It's a kind of very subtle and not sort of simple quantum mechanical evolution. We know what quantum evolution is. It's unitary time evolution. This is something else. And how do you get there? There's a lot of subtleties in between. Okay. So that's my half-hour review of the medical lecture you missed last night. All right. So, any questions so far? All right. Let us continue then. So let's talk now about a slightly different circumstance. Let's suppose I want to do the following. Let's suppose I have hydrogen. Here's the ground state hydrogen. And then we have the first excited state, which is split by the Lamb shift, the tiny Lamb shift. And then, of course, there's the 2p 3/2 up there somewhere. Okay? So this is hydrogen, what we've been discussing in the last few lectures. And suppose I want to directly measure this. I want to measure the Lamb shift. I want to know how big it is. It's a real test of quantum electrodynamics, because as we know, the Lamb shift is coming from the vacuum fluctuations. So I want to measure this energy. How am I going to do it? Well, I might want to do it the way we just described. Let me tune, some kind of laser source, if I can find the right kind of laser that, has this hard UV transition. There are tough lasers to me, but maybe, it's the 21st century. Yeah.
Then will you just shine it on like a bucket full of hydrogen, or how do you control?
Well, yeah, we need a vapor. We need a lot of hydrogen atoms. One hydrogen atom is going to be hard to measure. Actually, that's not exactly true. These days, you can track things. You can really focus on a particular atom. It's a different world than it was some decades ago. But there's a problem with this. One thing that what we've been discussing, and one thing you've seen in your homework, is that in order for me to drive this with an electric dipole, my So my interaction here, if I think about the interaction, as we'll discuss, is the interaction of the electric dipole of the atom with my applied laser electric field. Okay. We're going to come back to this. Remember, we started this really with the vector potential, and we got to see how we get to this. We haven't really discussed that, but as Lynn Susskind said last week, I'm a physicist, trust me. So my absorption, my initial state here is the ground state, and then, you know, I have some final states, have some matrix element. Let's say that the polarization is in the z direction. Let's call it polarization in the z direction. So this is the kind of matrix element that I would need to, that determines the strength of the transition, right? However, you know that in order for this matrix element to not be zero, I have to have opposite parity states. These have the same parity. I cannot go from two states with the same parity. I have to have opposite parity. This is zero. So you might say, okay, well, what about, as we'll see, go to the next order, quadrupole. Maybe there's a quadrupole interaction. We haven't talked about that, but we will, because we're going to talk about tensor interactions and tensor operators and all that stuff. And everyone will love to figure out what they're about in the semester. But as we'll see, that no matter what, it's impossible. There's no way. There's what's called a completely forbidden transition. You cannot go from L equals 0 to L equals 0. That is verboten. There's no way to go from a state that has no angular momentum to no angular momentum and absorb something. That's a completely forbidden transition. Yeah?
Is that because like a photon carries
some angular momentum.
Okay.
Absolutely. That's right.
Could you go from L equals 0 to L equals 1 to L equals 0?
Indeed, it could. So we could do that with a combination of an optical and a microwave. That's one way to measure it. You have to go that way. That's something we can do. And we'll come back to that in a moment. That's a kind of two-photon transition. In this case, one optical UV and one microwave photon. Or, as we'll see, maybe I don't do this to first order. I mean, this is a sequence of this to this to this to this. But of course, there's a little bit of a problem. If I directly go up here, we know this state can decay, and that might, you know, ruin my spectroscopy. So we would like to kind of avoid doing that. We don't want to really populate that state much. So another way to do this is by thinking about the higher order terms, which we haven't gone to. So the first order, for this problem, direct excitation from this to this vanishes. The first order term in my Dyson series is 0, okay? Because this matrix element is 0. So we have to go to second order. So let's take a look at that. We'll come back to this specific example in a moment, but let's just think about this generally. So we're looking at generally in the sense of the following. I'm driving the system with a single frequency, and I want to see what is the probability to get to here to here. Okay, that's a final time. The first possible non-vanishing term is the second order term in the Dyson series. Okay? So my probability to go from the initial to the final state to second order in the Dyson expansion is equal to minus I over h bar squared one integral from 0 to t, another integral from 0 to t dt prime. So that's the time ordering of my exponential in the second order. And then I have the matrix element of the interaction. And I can only get there through absorption in this case. We'll come back to all right, maybe I'll also let me write this out. Maybe let me be more general. Let me be more general. So, excuse me. Let's give this a shot. Let's see how it goes. Let's try to do this off the cuff, because I think it will be interesting. Right, so that's just the second term in the Dyson expansion, right? This is all in the interaction picture. It's important.
Should it be squared? Or absolute squared?
Let's talk about the amplitude. Okay, so that's I will ultimately square it. All right. So remember that these guys, each one of these guys, is equal to U0 dagger like that. Where this is the Schrodinger picture operator. That's how we go from the interaction picture to the Schrodinger picture and back and forth, okay? All right, that's just an aside to remember that. So how are we going to deal with this? Well, what we're going to do here to calculate this matrix element is insert in here a complete set of states. That's to say, these are the eigenstates over some index. These are eigenstates of H0, okay? So this is equal to the sum over the intermediate states right? Okay. Now, using this fact, we can re-express this in terms of our original Schrodinger picture interaction by applying the U0 and getting the phase e to the I f n t u f in the Schrodinger picture. And this is e to the I n I. Oh, one of these is a t prime times the matrix element m h int t prime I. Okay. All right. So now I have to decide, we're going to have this thing be of the form we had before. This guy, you know, this is my laser field like that, right? Which of course has the polarization that we called it in the z direction. And this thing has a e to the plus I and e to the minus I component, as expected. So we have a positive frequency component and a negative frequency component on this. Yeah?
What's this? I think you got one of the ket wrong on the second one. You have UM.
Yeah, sorry. It's messed up. Thanks. It should be U sub I. Okay. So, well, if we're going to, let's come back to the specific example. We'll look at some other specific example in a moment. If I'm going to drive the system to here, and I'm going to do it to second order, one way to do that is through a 2-photon transition. Instead of absorbing 1 photon and going from here to here, as we'll see in a moment, I can do that by absorbing 2 photons. This is what's called a 2-photon transition. So that's going to involve 2 kinds of absorption. So that's going to involve 2 terms, both of which are of the H plus type, 2 positive frequency components. When I plug in over here, there will be both a positive frequency and a negative frequency, a positive frequency and a negative frequency, but I'm only going to, for the moment, because I don't want to retain 4 terms, the positive frequency times the positive frequency. Zeke, you had a question?
Just real quick, so the 2 photons, do they have to be like bunched in the same state, or do they just have to be close together in time, or I guess it's not really relevant, but...
No, I mean, in this circumstance here, the temporal correlations of these are not known, because the photons are uncertain in where they are over the time duration of the interval. And then you can ask about photon statistics, right? In this picture of things, we haven't quantized the field,
Oh, okay.
right? We haven't really even thought about what that means. I mean, we use the word photon, but there's no quantum electrodynamics here. This electric field operator is just a classical field, right? So where the photons were in time, that's not really part of our description at this point. But ultimately, if I did quantize the field, then in some time interval, there better be a probability for there to be 2 photons in that. And that probability, you know, as one would see if we treated this as a classical field, would be a random Poisson distribution. If I did have a kind of non-classical source where photons were correlated, that can enhance this probability in ways that we're not discussing at the moment. All right, so we're going to only, for the moment, keep here the 2 positive frequency components. We're looking at this 2-photon absorption process. Okay? So with that said, my transition probability amplitude I have this integral over the first time, an integral over the second time up to the first time. And then I have at e to the I omega fm t and an e to the minus I omega laser t times that. That's the first term. And then I have an e to the I omega m initial t prime, e to the minus I omega laser t prime, and the matrix element between the intermediate state. Okay? Those are my terms. You buy it? Okay. So now I have to just do the time integrals. Okay? So rewrite this again. Sum over m So this first integral gives me e to the I omega, this is square, doesn't matter, but what the heck. Mi minus omega L t minus 1 divided by omega mi minus omega L in the denominator. Right? And now I have to integrate over t. So I have to be careful here because this still depends on t through the time ordering that we did. So let's put these two guys together. Well, let's just write it on the next line again. I'm going to cheat. I'm going to put this over here. So this is, I'm going to take out 1 power of h bar and write this as e sub m minus e sub I minus h bar omega L. That's the denominator over there. Okay? And now I'm going to combine this term. Omega Fm is omega F minus omega M. Omega Mi is omega M minus omega I. So when I add these together, I get omega Fi. And then I add that, and I get 2. So that's this term multiplied by that, and then minus what was there before, which was I omega Mi minus omega L. No, that was Fm. I know you hate me, but you hate me for many reasons. All right? So now I can do the integral again. Now we're up to the final time capital T. And this is equal to e to the I omega Fi minus 2 Lt minus 1 divided by omega Fi minus 2L. No, sorry, that's this guy. Integral this, and then this other integral is e to the I omega, and f minus omega L t minus 1 over omega fm minus omega L. All right? And so, now, if we tune this thing near to two-photon resonance, such that, coming back to the board over here, the sum of the 2 times omega L is near to the Bohr frequency associated with that energy difference, then this is a near resonant process. Okay? And of course, this guy is extremely far from this state or any other state, which means that first term completely dominates the process, because that second term here depends on the difference in frequency between one photon and, say, this would be the lamp shift, for example, if my intermediate state was considered to be the 2p 1/2. So this term is completely negligible, far from two-photon resonance. Whereas this term dominates. And that term, we again recognize, it's got some phase that we really don't care about. This is T times the sinc of the frequency difference between those guys. And then there's a phase out front, but I don't really care about that. Right, it's phase. Rewriting this by writing this. I've got the I, of course, and then there's a T, and then there's a 2, and then there's another 2, and then I put a T up front and do all that. Doesn't really matter, this algebra. I'm a physicist, trust me. You can go through the algebra. It's the same algebra we did. Okay, let's take this whole messy thing and write it more cleanly in the front board. Okay? Okay, so near this transition amplitude is equal to the sum over n. The final intermediate divided by E final minus E initial minus final minus, sorry, m, much more, times sinc omega final initial minus 2 the laser t over 2 times t. All right. What do we see in this expression? Well, one thing we see is this is just like we had before. This is a 2-photon resonance. So this sinc function is of the sort that we saw before, where it's centered where, in this case, where the laser frequency is half, exactly half. So if this is my final state, this is my initial state, I have 2 photons, which, when this frequency difference is twice this, we're on resonance. We're on 2-photon resonance. But the way in which the 2-photon resonance happens involves this sum. We don't have a direct coupling of our interaction directly from the initial state to the final state. But we have first going to these intermediate states, and then from the intermediate state to the final state. Now, how is that possible? Well, we didn't do anything other than just expand the unitary time evolution operator in a very fancy way. This is just time evolution. But this is often given a semi-realistic interpretation, which let me describe to you. And we can decide whether this is actually a meaningful way of saying what's going on in reality in the world. Okay? What is often said is that I have made a virtual transition. Now, what's going on over here? Let's go back to the backboard for a moment. Let's think about this in the particular case of measuring the latch. Okay? Now, in this case, I want to go from the ground state, the 1s 1/2, up to this excited state, the 2s 1/2. I can't get there directly with a 1-photon transition, but I can get there through this 2-photon transition. Now, when I sum over the intermediate states are connecting the ground state through this interaction Hamiltonian to other excited states. So there is a matrix element, for example, between this and this, or between this and those have probably the dominant matrix elements. So what we would say is that I created a virtual excitation, say to the 2p 1/2. I created a virtual excited state. It's not really in that excited state, it's only virtually excited state. You hear the term virtual all the time. You know about virtual perturbation. It's exactly the same thing. Okay? What is going on? Well, this doesn't conserve energy, right? It doesn't, in the Fermi golden rule sense. I can't get from here to here with one photon, because this energy difference is very different from that single photon. So it seems to violate energy conservation. So how in the world did I get there? Well, the language that people like to use, and I don't know if I'm people, is that, well, I'm allowed to go to that state as long as I do it for a short enough time that there is a kind of time-energy uncertainty principle that says I'm allowed to violate energy conservation for some tiny amount of time, because then there's a big uncertainty in energy. Okay? So what they would say is that I'm only kind of cheating the universe out of the energy that it so deserves for some time that is consistent with the time-energy uncertainty principle. And then I put it back, and the universe never noticed that I stole that energy from the system. Okay? That's the kind of picture. And we see that if we go back to the front board. The degree to which these different terms contribute depends on this energy denominator. This is the energy deficit between the photon that I've put into the system and the energy that I got from exciting virtually up to the intermediate state. So the bigger that energy deficit is, the smaller this contribution is to the sum. Okay? So one distinguishes between real transitions and virtual transitions. Now, editorial comments. Charlie knows these. This is bullshit.
Why don't you make?
I didn't try. What's real in quantum mechanics? What's virtual? I mean, it's all just quantum mechanics. It's not, there's this desire to think, as I say, that what's real there are energy levels, and those are the real things. And things just go from here to here to here to here. And if I can't really go to there, well then I must have sort of been doing something virtual. But what I would say is this is just representing is the fact that I have coherent quantum dynamics. I'm allowed to be in a superposition of states because I'm never violating conservation of energy. I've done things with a Hamiltonian. And the Hamiltonian is time dependent. I'm putting energy into the system, right? So what's happening here is just intermediately, I'm in a coherent superposition of states. I've driven through my, if I come back again to the back board, I am well off residence between this and this, but that's okay. I can still have some amount, there's going to be some coherent superposition that I have driven between, say, these two states, creating a dipole, an induced dipole moment. It's a very, very small one. And that induced dipole moment, then I can have another induced dipole moment. And those two dipole moments in a nonlinear optical way, it's not linear optics, it's nonlinear optics, can drive the system up here. So it's coherent quantum dynamics. The desire to think about this as these are processes happening in the world is our desire to make sense of quantum mechanics. And that becomes especially true when we start thinking about quantum field theory, when these processes involve particles. And we really want to think about particles as stuff. They're there, they're not there, they're virtually there. We wrap a language around that to try to make sense of the world in some way, right? But whether we, I don't want to completely, it's to some degree a useful language to talk about real excitations versus virtual excitations in the following sense. Suppose, let's go back to the suggestion that you had, Stephen, of what if I went directly up to here and went to there. So this would be a sequence of two real transitions. I truly go up here, and then I truly go up there, as opposed to here where I only virtually excite this state and then come up here. If I do the process this way, as I said, there's this problem of that this guy will decay, and then it's much harder to measure things. On the other hand, I could imagine the following kind of situation. So here's my, I'm just going to draw these levels. Instead of driving directly, I can go off resonance by some amount with two different colors, right? So this is my laser and this is my microwave. What we would say is I do a virtual excitation here and then go up here. And of course, because this is way closer to resonance than this will be a much stronger transition. Depends, of course, on what the intensities are, because as we said, the degree to which you cheat the world out of the energy it deserves, in some sense, determines how strong this transition is. But in this case, this is another kind of two-photon transition involving one laser photon and one microwave photon, which we would say we would create a virtual excited state. Here, I virtually excite this, and then I come up here. Or I could think about other kinds of situations. We do this all the time. Suppose, let's say, here's my hydrogen atom again, okay? And now I'm going to draw in the hyperfine structure. My hyperfine structure has this, 1.4 gigahertz splitting in the hyperfine ground state. This is my F equals 0. This is my F equals 1. And suppose I somehow prepare this just in that magnetic sublevel, and I want to drive it down here. And one way to do that is apply a microwave here, but I can also do it in the following way. With two different colors lasers that are separated by 1 point. Just modulate the laser, one laser being by 1.4 gigahertz. So I go up, virtually excite this state, and then drive back down without ever populating this very much. And in that sense, I can coherently drive from here to here without exciting this state. This is what's called a Raman transition. It's a different kind of two-photon transition involving absorption. So one of these would be H plus, and the other would be H minus. Okay. You do that all the time. So just to conclude, this kind of picture of these intermediate states is often to do time-dependent perturbation theory, especially when it gets very complicated and you get to very high orders. One has a kind of diagrammatic method that takes into account all these terms in the Dyson series. And that diagrammatic expression of this are known as Feynman diagrams. So in a Feynman diagram, what's going on is that each matrix element, fundamental matrix element that connects the states has a particular kind of graphical description. So for example, in our atomic thing, it's a very simple thing. I either absorb a photon or emit a photon, right? So I can have the circumstance, for example, where I start in the 1s ground state, and then I absorb a photon, and then I'm in the 2p, 1/2 photon. And then I absorb another photon, and then I'm in 2s, 1/2, right? Now, of course, this intermediate state, we would say, is a virtual excited state, because these photons that came in are of energy that's different than the energy difference in this. So this would be a virtual excited state. And then I went from this virtual excited state to this state, right? That's what Feynman diagrams are. They're different terms in the Dyson expansion. And that's in quantum field theory, that's how we try to calculate things like the correction to the anomalous magnetic dipole moment of the electron due to its coupling to the electromagnetic field of the QED. It's just this. All right. Well, conclude for today and pick it up next time.